you, Min, and I apologize for the technical difficulties. So yes, my name is Chuck Wolber. A little bit about myself. I have a BS in mathematics from Washington State University. I am a contributor to several early editions of the Red Hat Linux Bible, and I'm the co-author of a book called Linux Toys. It was published a long time ago, so it's out of date. It was a lot of fun to write. It's had a bunch of fun little Linux based projects. Sounds like I was also the president, and I'm now the benevolent dictator for life of the Tacoma Linux users group. So I've been in the Linux community for a long time, and then I've got 20 years as a Boeing software engineer. I was inducted into the Boeing Technical Fellowship in 2022. Which in a lot of other companies, that's like tech principal or something like that. And then if you flew on a Boeing aircraft, you've probably flown on an airplane that has a design certified Linux platform that I helped develop. Most of the work I do is in non-real-time Linux. There's when people think of avionics and stuff that flies in airplanes, their mind probably always goes to real-time stuff. And there's a lot of that. But there's also a surprising amount of non-real-time stuff that flies around in airplanes. And one of my early projects, it was a non-real-time embedded system. It was something called the electronic flight bag. This is a picture I saw in the popular media. I got permission from Simone Biles' agent to post this, to use this. Simone Biles and Michaela Skinner are sitting in a 787, a Boeing 787. And then if you look just to Simone's left elbow, there's a display there right behind the captain's yoke. That's called an electronic flight bag. I spent a lot of time working on that system. That was one of the first embedded systems I worked on at Boeing. I've moved on to a lot of other stuff, had a lot of fun. There is a Linux OS on that. There's also a Windows OS on that. And then if you're curious, you can Google, there's actually a lot of stuff online about it's called the Class 3 electronic EFB. There's a lot on that. So let's go in to some basics. First of all, quiz for you. Can software be certified? So when we're talking about certified, I'm talking about in aerospace, aviation. Can a piece of software be certified? Is it true or false? Okay, so it depends. It's not true or false, it depends. So only software systems can be certified. And the certification criteria varies depending on the airframe. So an older airframe is going to have different cert criteria than a newer airframe. And it's a little muddy even there. We've actually got certification experts. I'll talk about those in a bit. But as far as systems go, software systems are made up of many different software components. So if someone were to tell you they have a certified Linux kernel, they're probably trying to steal your money. There's no such thing. You can have certification artifacts. You can have elements that help you use that Linux kernel in a full system, but by itself, it's not a system that is certifiable. When we combine all these things together into a system, it's called an airplane part. Just like a hunk of metal, it's got a part number and everything that goes on an airplane. It's very carefully controlled. It is just an airplane part. We have engineers at Boeing called system engineers. This is something prior to coming to Boeing I'd never heard of. And they're incredibly bright people. And they've got this encyclopedic knowledge of how all these systems interact. And so it is an entire engineering discipline to combine systems and know how they interact. Some of these people, particularly the ones who have been at Boeing for a long time, it's just really difficult to see them retire because they just carry so much knowledge of the history and what happens, how all this stuff came together. Fortunately, it's really well documented and stuff, but it is just an incredible amount of work and effort. And I'm in awe of these system engineers who put these systems together. So I am a software engineer. I work on discrete parts of systems, but we actually have engineers that combine systems. A software system, okay, is once it's released, if we want to change it, we do what's called a software change impact analysis. Sometimes that may require us to say we have to do a complete restart. We've just changed so much, or sometimes it's just a very discrete, small amount of change. Typically with systems that you update every couple of years, it's just in general going to be a complete restart. But that's what you find out in a software change impact analysis. So in the ground-based world, when you have 1.0 out in the field and you want to release 2.0 or 1.5, whatever, typically just go ahead and do it, or you'll go through a whole test regimen. In aerospace, you have to go through a change impact analysis, see what's changed since then, and see how much work you have to do to recertify. All right. Okay, so this is a not to scale idea of what the regulatory environment looks like. So just like we have system engineers at Boeing, we have specialists who just do nothing but specialize in regulatory framework. And we call them engineering unit members, or in the past, they were called designated engineering representatives. These people work from what's called an ODA, Organizational Designation of Authority, from the FAA and the EASA, they have the power of the regulatory agencies to certify or tell us when we're doing it right or when we're not doing it right. So what I'm trying to give you an idea of here is, and these people are like lawyers. It takes a long time to get, they call it your ticket, to get your ticket to be an engineering unit member, EUM. And they are also very, very intelligent and very great to work with, because they make sure that all of our I's are dotted, all of our T's are crossed, and that we cross the certification finish line exactly the way we should. Such that if a regulator from the FAA or EASA wants to come in and oversee us, everything's in place. They make sure that we're all set, ready to go. So we delegate that authority all the way in the United States. We delegate that authority all the way up from the U.S. Constitution, which Congress derived their powers from the Constitution, which then created the Air Commerce Act, which created the FAA. There's a similar history in EASA and other national airspace regulatory agencies. They are the ones who create what's called the objectives. The objectives are not what we use to certify software. We can use the objectives to come up with our own way of certifying software, but that's not efficient. Let's just say that. The aerospace industry, in cooperation with all the regulatory agencies, comes up with a consensus of how to meet those objectives. And then nonprofit organizations like RTCA Radio Corporation, no, I'm sorry, I'm blanking on the exact acronym. RTCA is a nonprofit standards body. EuroK is another standards body. And they work together and they create these standards documents like DO-178C, that's the RTCA version, or ED-12C, which is the EuroK version, and so on and so forth. So DO-178C is the one we work out of most. That's software considerations for in airborne systems and equipment certification. We also have software tool qualification considerations. So you would imagine that if we're going to rely on a code generator, or we're going to take credit for what's produced in a compiler, we have to qualify those tools. And there's an entire process for qualifying those tools. There's also object-oriented. I put some other stuff on here. Object-oriented, if we use object-oriented code in a high criticality system, we have a whole standard for that. And then the most recent one is DO-356A or ED-203A. That's airworthiness security considerations. That all has to do with a brand new thing. Generally, it's like negative requirements, how we prevent something from happening. Typically for DO-178, it's how you assure something's going to happen the way you expect it to. DO-356A now is getting into the realm of how do we prevent something from happening. All right. So I'll talk mostly about DO-178C. That's the great granddaddy document that most of us cite and work with. And in fact, in job postings, you'll even see experience with DO-178C. I had the great privilege to work with one of the original authors of DO-178, contributor to DO-178B and C. He's one of my chief engineers. He was also the chief engineer on the electronic flight bag. I learned an incredible amount from him. It was a real privilege. And I learned from him that this is industry accepted guidance. It's not the only way to certify software, but it's the easiest way, and it's the industry accepted guidance. And if you follow that way, it makes your life a lot easier. And it creates what's called a means of compliance that really boil down to two very simple sentences. Okay, every system on an airplane addresses or reflects or creates or manages some sort of a hazard. So the first question is, does the design that go into that system adequately reflect the hazard? And then the second question is, now that you've implemented the system on that box, whatever it is, does the implementation match the design? All the artifacts you create, they have to reflect the hazard, and they also have the implementation has to match the design. It seems simple, of course it's not. It's most of the work you do in software and aerospace. It's broken up into 5 levels, A through E. A, of course, is the highest criticality. We call that catastrophic. It's a catastrophic hazard, and all the way down to level E, which is no safety effect. And as you would imagine, it's the blue bars are a relative indicator of difficulty. In catastrophic, we have 71 very complex objectives we have to meet. 30 of those are with independence. I mean, you have to demonstrate that the team that created and managed the hardware is not the same team, was completely independent from the team that met the other objectives, all the way down to DAL-E, where there are no objectives, nothing even with independence. There's just no safety effect, so there's not a big concern. We call that A through D, we call it design certified. In other words, you're certifying the implementation matches the design, and the design adequately reflects the hazard. So there's a transitive dependency there. And then for E, or DAL, design assurance level, DAL-E will say no safety effects. So we'll call that operational approval. What that usually means is during a certification flight, when the regulator, they'll just look at it and say, yeah, that does appear to work exactly as we say. There's no way it could have any safety effects, so we're good. Obviously with D, C, B, and A, there's a lot more scrutiny. All right, so how do we meet the burden outlined in A through E? And by the way, even for E, we'll do a lot of DAL-E projects, and we'll say we're gonna just do it to DAL-D specifications. It's better that way, because what you actually find is DAL-D has a very close relationship with a lot of best practices. Even non-aerospace software engineers will go through. It's a lot more rigorous than, you know, a lot of the projects, but when you scrutinize it, you can sort of see the logic and the best practices in there. So even DAL-E projects will be done with DAL-D level of rigor. So the burden of proof is on the engineer. The regulator is not going to tell you how to do your job. They'll tell you when you're doing it wrong. They'll tell you when your chosen approach is not effective, not done well enough to meet the hazard, and your design doesn't reflect the your implementation doesn't reflect the design. But they're not going to tell you how to do your job. So the engineer, the burden of proof is on the engineer. Simpler, of course, is a lot easier to prove. So when you're trying to convince the regulator that you've done your job, you've met all the objectives, it's just easier to be simpler. These regulators, they are very smart. It takes a lot of effort to get the ticket, but there's just a lot to go through to certify something. So keep your environment and your design, your implementation, keep it simple. It'll make the process to get through certification a lot easier. And remember, regulators and software engineers, they are humans. As hard as that is to imagine sometimes, they are human beings. Everybody forgets things. We have to document things. Okay, so no matter how intelligent the person is, if you don't have a real well-designed environment, people are going to trip over non-obvious and confusing things. No matter how gifted the individual is, you just want to try to remember that these are human beings you're working with. And of course, one size does not fit all. That's the acronym. There is always one. There's more than one way to do it. Meaning all the things I'm going to talk to you about today do not represent you know, a specific, like DO-178. They're not a specific means of compliant that thou shalt. They're not written in stone in a RTCA or EuroK document. This is just one way of doing things that has a great deal of history behind it that actually works. You may choose to do it differently. You may find things that I'm talking about problematic. That's good. A lot of what I'm trying to do is also start a dialogue, because there is some community interaction with the Yocto OpenEmbedded project that they do some great stuff. We also have some stuff that we're, you know, the open source community want to open source, and it helps to sort of make the case for things that work and how that will work with other projects. Okay, so for this environment I'm talking about, we really want to view human error as a symptom of bad design. And I'm not talking about the certified product that goes out the door. I'm talking about the development environment that developers use. Okay, we want to try to avoid human error. Like I said, that's a symptom of bad design. So it really needs to be able to support hundreds of internal developers. It really does need to support tens of embedded distributions. I actually think that's probably closer to hundreds of embedded distributions, but I didn't want to go overboard. And it does need to support distributed application layer development. Some people would call that product lining, where you can delegate to separate teams in the Yocto OpenEmbedded environment. You call those meta layers, right? You need to be able to support where those teams may have separate release processes. They may have separate timelines and schedules and budgets and those kinds of things. So it has to support that and allow everybody to work comfortably, which means it needs to be simple. It really does need to be turnkey. The day one developer thing, it needs to be taken seriously. So the set of documentation to get some developer going needs to be about less than a page, ideally a post-it note. The rest will just sort of come to you as time goes on. It's got to be repeatable. Everybody's experience has to be the same, meaning the build system has to have the same experience as every developer. The developer using a Mac has to have the same experience as the developer using a Windows machine, et cetera, et cetera. Has to be consistent. So when you're trying to do a thing, has to have a consistent way of building it. In other words, if you know Yocto OpenEmbedded, I'm talking about like BitBake recipes, right? No matter what you choose as your application building method, make, CMake, Ant, Maven, Gradle, all those things, it has to have a consistent way of integrating into the final product. Obviously, it has to be extensible. Think pipelines, either BuildBot or GitLab runners, those kinds of things. It's got to have something that's extensible so that we can inject other things like static analysis, automated testing, create environments with virtual machines. It's got to be configuration managed. You shouldn't have to have a huge number of meetings with developers and constantly remind them of, oh, you're doing this wrong, you're doing that wrong. That's a symptom of bad design. So a lot of the work you do should be hidden under the covers. It shouldn't be anything you have to tell anybody about. It just, when a developer does a git pull and updates their repository, it should just work the new way without really having to tell them much. Maybe a little, but not much. Of course, it needs to be traceable as well. Every change has to be traceable to some sort of decision process. So that's all reflective what I'm going to talk to you about here. So let's talk about distribution building, Linux distribution building in particular. This is going all the way back. This is, anytime you've ever used a Linux distribution, this is more or less how it's done. This is a system also that I set up originally before Yocto OpenEmbedded even existed back in the early 2000s, because there was no way to do embedded Linux development easy way for the stuff that I was doing. Like I said, I worked in the non-real-time space, so we had a little bit more design space and levity than in a real-time environment. So typically you would have identify package level, identify what functionality at the package level. In Red Hat Enterprise Linux or Red Hat Linux, those would be RPMs. In Debian, it'd be dpackage. Embedded now use IPK. It's a great embedded package format, and you design you create all your packages, and that's in RPM, for example, you check in your spec file. Debian and IPK, you have similars, and then you have to build it. Okay, you like actually, I'm getting ahead of myself. Step 0, you have to generate native tools. So you want to build your compiler. You want to build all your linkers, those kinds of things. Even if you're building for like for example, if your target destination is x86, even if you're on an x86 computer, you still want to generate an intermediate x86 compiler, okay? Because the distribution supplied compiler is specific to that distribution. It's going to generate code that's specific and tailored to that distribution. Now, it's generally workable, but what you want to do is build a compiler in an environment that is specific to what you're delivering to. And so you want to generate native tools that way. And then you iterate through all of your chosen packages, build intermediate products, which is, those would be your package, they turn into binary package at that point. And then you generate so step 2 is you generate a raw root file system in a virtual machine. That would just be a sparse disk image, okay? And then step 3, you would imagine you would do equivalent to chrooting into that. You'd mount as a loopback device, then you chroot into that sparse disk image, and then you just iterate through all your packages and you install them. And packages have dependency management, so all that graph, that complex dependency graph, should be worked out for you by your package management. And then at the end, you've got a rootfs image that you can then roll up into an ISO, or we have an industry standard format in aerospace called ARINC 665. It's just another package format. And that's your final image that flies away. And then you've got a scheme for data loading that on an airplane. That's the overview of how distribution building is done in a nutshell. It is effectively done the same way under the hood in Yocto OpenEmbedded, but it does a whole lot more in a far more elegant way. So I was more than happy to throw away years and years and years of build system development to switch to Yocto OpenEmbedded, because it was just better. It was just better. And it's also had a lot of industry support, a lot of good ideas, a lot of diverse opinions went into this. And what we got out of it was something very, very, very good. And I got to hand it to Richard Purdy. He is a phenomenal architect. I think the project is in great hands. I will also remind everybody, please support him and the project and the team and all the contributors to Yocto OpenEmbedded. It is totally worth it. So I'm not going to go over too much. I stole this from the incredibly good documentation, by the way, from the Yocto OpenEmbedded project. But it's worth taking a look at it. It goes, you can see evidence of sort of what I described on the previous slide in here. But there's a whole lot more, including automatic SDK generation, license auditing, all those kinds of things. Okay, so just to give you some background, if you've never done a Yocto project or worked with the distribution, this is what the BitBake recipe, this is what the consistency part looks like. So it doesn't matter how, this is POP-T. I just stole this at random, the POP-T binary source build. Doesn't matter how it's built. In this case, it's auto tools, okay? But it could be any form of building, and there's usually functionality within OpenEmbedded or Yocto that has a way of building. So you'll just inherit that functionality and you'll through in your recipe. So the recipe isn't huge. Most of the work for building this is abstracted away in the make files that come with POP-T, for example. Or if you so choose, if you've got sort of an in-tree source code, you can actually put your entire build in the BitBake recipe as well. That you probably shouldn't, but you can if you want to. And at the very end, that last line, BB class extend, that says that POP-T is actually going to be one of the native tools. So that's one of the benefits of also Yocto OpenEmbedded, is that it will, first thing, like Carl Sagan said, if you want to build apple pie, first you must build the universe. OpenEmbedded, Yocto OpenEmbedded does a similar thing. It will, first step is it will build all of your native tools, and then it will build all the way up through a very complex build graph until it finally gets to POP-T. It, of course, caches all those artifacts. So the next build doesn't have to recreate all the native and all the dependencies on POP-T. And it also, there's dependency declarations, just like with RPM spec files and Debian D packages. So it's got what you should expect. License auditing is facilitated. Anytime there's a change, you tell in the recipe what your license file is. Anytime there's a change to the license, you're going to be notified in the build. That's really important. Of course, also the checksum, of the source bundle is listed in the recipe. So if bad person hacks into rpm.org and alters the source bundle, that's going to trigger a build error, and you'll know about it. Okay, so the typical workflow, you can do this at home. You, on your Linux box, or you have WSL, Windows Subsystem for Linux, which is a Yocto build, by the way. You can clone the Pocky, which is the reference implementation, and then you just source the build environment, and you type BitBake, core image, full command line, for example. Wait a few hours, your room may be a little warmer, and then you can use, it's got a run QE, it's got a QEMU wrapper all built in. So you can just run QEMU, no graphic, and then the image, and voila, you've just built and run your own Linux system in 4 or 5 commands. It's pretty straightforward. So let's talk about the environment. Let's talk about what did and did not work. Git Sub Modules did not work. And we'll talk more about that. Out of tree source code did not work. And something we call hybrid builds, that did not work. So everybody's got an opinion on Git Sub Modules, and I'm not here to tell you you're wrong. I'm here to tell you that it did not work from my experience and my team's experience. It's okay to disagree, particularly with Git Sub Modules. It didn't work for us because it was too complex. Every objection to Git Sub Modules is always seemed to be overcome by additional complexity. When something didn't work, someone would say, well, you just need to, and it is just more complexity. It violates the do one thing or the single responsibility principle because it obscures the boundaries between local and upstream code. It's very difficult to CD change directory into a Git clone and surprise yourself and find out, oh, actually, I'm in the OpenEmbedded core directory, and I shouldn't be changing that. How do we maintain control over that? So it obscures the boundaries. It's, again, you can always work around these things. So there's nothing that says this is black and white. There's a lot of nuance available here. It made things a little more complex. And it's just, at the end of the day, it was too little benefit. A curated environment, you can manage it a lot more simply. And I'm going to go into the ways that it's managed a lot more simply. Out of tree source code. So if you look at a typical meta layer or like OpenEmbedded core, they do a really good job of it's just a collection of recipes. And each of those recipes has a source URI or a URI in the recipe itself that points to upstream source code. That's when you run the build and it build invokes that recipe, it's then going to go download or find that recipe source bundle and build it in. And that is a really neat way of using distributed development to work on isolated discrete. This is a way of corralling in one repository thousands of different projects. You're not going to corral all the GNU project along with a bunch of BSD engineers and into one repository. That's just impractical. So out of tree source code works great for non-internal layers, but when you have one team managing hundreds of different recipes and sometimes thousands of different recipes, it doesn't work to have thousands of different Git repositories that a team has to go into and manage, because you also have to remember those have to be tagged and curated and listed in regulatory documents. So it becomes burdensome and onerous to do that. So in-tree source code has a practical use. It is totally impractical, and I get why Yocto OpenEmbedded project does not do it as a general course, but there is a use for in-tree source code, particularly internal development where you have thousands and thousands of packages that have to be curated. Now, those can be broken up into separate repositories, meta layers, core, that kind of thing, and that should be done. But that's why out-of-tree source code really doesn't work internally. And then, of course, hybrid builds. I've seen this done where there's a portion of the build is done with a Yocto OpenEmbedded build, and then another portion is done using some other method, and then you've got a shell script that bolts them together and do an integration step, and what you have flies away. I saw that done. It does not work. You have to do two separate tools for everything. Yocto, OpenEmbedded, BitBake, all that. It does it way better. Just roll it all into one, create BitBake recipes. You'll be glad you did. All right, what did work? Virtualization, mirroring, pinning, shimming, BitBake wrapper, building everything from source, recipe generation. I'm going to go over each one. So virtualization. Virtualize heavily, even at the developer desktop. You can still use Visual Code. Use the SSH plugin. It works great. Okay. Basically, you start with some baseline features. That's your kernel, your architecture, your kernel, your glibc, probably your init. Okay. That's you can imagine you can create an include file. Okay. From a BitBake recipe include file. You'd imagine you would do that. Sometimes it's more complex than that. Next, you add some next you add some operational features. That allows you, and that's your image recipe for something that can fly away and be delivered onto an airplane. But you can also, and we've done this, take that same image and create some BB class functionality to turn that into an operational appliance. So you've got a simulator that you can build trivially from the image that also you're building to fly away. And yes, we do hope to open source that. We're working on it. For the developer environment, you can take those baseline features. You can add developer features to another image. And that you would imagine is your compilers, your man pages, any other utilities you want, nice to haves, simulators, Vim editors, all that stuff, okay? That also in the nightly build can generate a build and development appliance. We started out originally back in the day in 2017 using Ubuntu 16.04. That was sort of our bootstrap. We built the first build dev environments using Pyro 2.3, then threw away Ubuntu. We just threw that away, didn't even need it. And that was our virtual machine. Then, like Matryoshka dolls, we used the Pyro image to build the THUD image when we upgraded to 2.6. And then we used the THUD image to build the hard-on image. And that's what we're on right now. These release cycles last a long time. With the build development appliance, you can use that all over the place. You can deploy it either locally under VMware or in an EC2 instance, running BuildBot. You can use Vault as your credential store, and then use that to run a build precisely the same way a developer would do their build using either Vagrant or QEMU or some other hypervisor on their desktop. And it's the same steps. There's a provision stage, there's a build stage, and then a developer's not going to do a deploy stage, but they may want to deploy to a bench in a lab environment. So there is a bit of a deploy stage, even if you're the developer. Virtualize everything. Do not work on your desktop. It does not work out well, but there's always a compromise. Like I said, you can use Visual Studio Code with the SSH plugin. It works beautifully. You wouldn't even know you're not on your desktop in that case. Mirror everything. Okay. Now this is built in to the Yocto Open to the BitBake. It's built into BitBake. Use the pre-mirrors BitBake variable. So that hijacks the source URI in the BitBake recipes and pivots you to wherever you're storing internally all your source. Because upstream source tends to disappear over time, and aerospace has a burden to be able to rebuild. And that means even if we have the binary, we still have to show at any time while it's in service that we can go from source code to that binary, and we have to be able to demonstrate that we can do that at any time. The rest of the terrestrial world just assumes they can move on from 1.0 to 2.0, and by the time you get to 6, version 1.5 is now missing from the internet. Happens all the time, particularly with NPM, right? It's a very difficult package format to work with that way because they expect you to sort of just roll forward with an incredible amount of change. That doesn't work, particularly in aerospace. So mirror everything. We use GitLab generic registries for that. I can't imagine what GitLab engineers would say if they saw us. We have a per release registry entry, and sometimes they get to be 20, 30 gigabytes in size. We use project variables that we source into the virtual machine environment, unbeknownst to the developers, that point them to the right registry entry. And then we have ways of switching those if they switch to another branch that uses a different release. That's all built into the environment. And then of course, obviously recipes validate, source bundle checksum. So again, like with the internet, even upstream in our local registry, we keep all that intact. You also want to mirror the repositories themselves. These mirrors need to be read-only, and they need to be bitwise identical to upstream. This is part about keeping it very, very simple for developers. Keeping it very simple so the certification process goes off without a hitch. These are cloned. We do namespace them mirror hyphen. So it's obvious, that should be obvious to the developer that this is a read-only environment. Although if there's an accident and they try to make a change and push where it's hosted, GitLab internally will obviously reject. It's all set to not allow any pushes. And then these are cloned automatically in the build development appliance, so developers don't have to worry about this stuff, and they're always pinned on a per distro basis, and I'll get to that. And then they're periodically updated and managed, and we'll talk about that here in a few slides. So let's talk about pinning. So when you have all these dependency repositories, you need to make sure that they're always in the right place for every developer at the right time. And when they change, you need to make sure there's oversight of that change and it's carefully tracked. That's part of the traceability argument. So we used to have another solution to manage the pinning, but Alexander Canavan created a really neat utility called setup layers that is now the one to use. You keep a JSON file in your project distro repository, And then setup layers consumes that and makes sure all your repositories are cloned and checked out to the right hash. And then a project administrator of some type would periodically update those mirrors and then check in a change to setup layers.json after the changes were reviewed by CCB. Change control board. You may not, agree with upstream changes, so you can override some of those with the BB append mechanism. BB class, you cannot override those changes, so we had to come up with a concept called shimming to override those changes, which we'll talk about here. So shimming is a way of maintaining a patch set on a per distribution basis that allows us to keep the mirrors, internal mirrors, pristine. And that basically manages divergences from upstream. That's a custom patch set that's managed. And then periodically, for anything non-proprietary, after a period of testing and refinement, what we'll want to do is submit those upstream to the project so they can be, we can remove those patches from the project distribution. That also allows us, even once that's pushed upstream, we can remove it from project distribution. Like I said, we have to do old builds, be able to do old builds. So when we roll back in time, we pin to an old version on all those mirror repositories, that patch will suddenly reappear, of course, because it's Git. And so you have a completely coherent build that never changes, despite the fact that we have a great deal of change going on upstream and locally. It's been asked that, why don't you just rebase instead of maintaining this patch set? I'm going to be a little short on time, so I will try to get that at the end when we have a QA, but there is an answer for that. We'll talk about. There's two approaches to this. I like to say that I am the type of person who would never mount their bicycle on the top of their car, because I'm probably going to go through a low overpass and destroy my bike. And that's why I prefer approach number two. Approach number one says just reset all the mirror repositories and apply all the patches in the right order. But I may be working in that mirror repository, so I don't want to destroy my changes. I, as a, let's say, project admin, we wouldn't expect a regular developer to be working there unless they're trying to fix something that we're now going to have a shim patch. Otherwise, what you do is you just do apply the patches in reverse, and then you apply all the patches in regular order, and you just ignore the reverse application, but you pay attention to any errors in the forward application to see if you have to error out. Very rarely ever happens, so developers never really have to worry. But there's also a backup plan if that happens as well. We print that on the screen. Okay, so the last but not least in putting all that together is you have to create what's called a BitBake wrapper. So all the innovations I talked about, you're not going to have a developer type those in by hand. That's very error prone, not worth it. So the wrapper is built in to maybe an admin or maybe a infrastructure repository, whatever, however you want to do it. And you put like BB, you could call it, put it in your path, and you say BB, BitBake, and whatever command you want to do. Under the hood, what it's doing is it's you might want to do a pre-flight check, make sure your environment is properly provisioned, there's sufficient resources, make sure you're running setup layers to make sure your mirrors are cloned and pinned, your shim patches are managed however you need to. Maybe you have tooling, like you're going to use build tools, for example, or maybe you're not. And then you're going to source OE init build env and stuff to source in the BitBake environment. That's all happening within the space of the shell script. And because we're building industry standard packages, those packages, image packages, those packages always have to have a different name. So we have to pass through some variables that ensure there's uniqueness to the naming. Okay, and so the developer workflow, basically on day one, developer, flow in the project repository. If they're using a Vagrant, if you're using Vagrant to bring it up, you don't necessarily have to, but if you're using Vagrant, you just Vagrant up, install the Visual Code plugin, and then through the terminal or a Git bash, for example, you can just BB BitBake operational image. That should only take you ideally an hour, maybe two if you have trouble with your SSH keys. That's really all it would take to get started. And we tell developers, your first time you run this, you're going to cache the build. So day one, read some documentation, play around, do something. And then when you get home, run this build. It's going to run for about 12 hours. It's going to cache, put it in the coldest room in your house and it'll warm it up. And then you'll have a cache build. Okay, build everything from source. Other than host tools, no pre-built binaries. Now that's not always true. Everybody always has that one thing that is a binary, and you just need a BitBake recipe that says pick and place. But otherwise, you want to build everything from source. That allows you to use the incredibly powerful architectural tools you can build for other architectures within Yocto, OpenEmbedded. Always just militantly, we need to build from source, create the BitBake recipe, do the work. So it leverages the full power of BitBake, shows you your build map, your manifest, your CVE check, tells you if you have to worry about vulnerabilities. And then let's see, like I said before, your developers are going to initiate your shared state cache because you're building everything from source. And then for nightly builds, you always want to start from zero cache. We have seen instances where you cannot trust the cache over time. I mean, most of the time you can from a developer standpoint, but for the official build, that build script's going to make sure you start from zero cache. Start from zero, and that's okay, because that's going to run overnight on a very powerful machine. Okay, and recipe generation, always try and template especially for like NPM, and DevTool is really good recipe tool that comes with in the I think that's the Yocto ecosystem. Comes with a tool for managing recipes, and it has some templating for NPM built into it. I'd like to see other things like Python modules and Maven, Gradle, Ant, stuff like that. I'd like to see a tool that universally creates BitBake recipes from whatever tool you're using to build. We have created a lot of our own template scripts that will, for example, Maven was the last one we just went through, created a script to create thousands of Maven BitBake recipes, and so on and so forth. It's very labor intensive at first, but it's very easy after that. You can just add more Maven stuff into there, or more Gradle stuff. That's what you get in a very mature environment. Every development trend is eventually reflected, and so rather than have to rebuild, well, that one uses Maven, this one uses Gradle, just roll with it. And BitBake allows you to sort of roll with it without having to do a whole bunch of giant changes. And then this is the last slide. Some of the unsolved problems that I'm hoping to solicit some help for is distro switching. So if you're lucky as a developer within Boeing, Linux developer, you just have one distro you're focusing on. But if you have multiple distros, you got one build dev appliances. What's a really good, efficient way of pivoting between focusing on one distro or the other? There are project variables sourced into your environment. There may be subtle differences in, I don't know, like glibc or something like that. And your build dev appliance doesn't necessarily have to have perfect fidelity with the glibc or kernel, obviously. You can diverge from that. But when you're trying to run something in a Linux environment like your build dev appliance, it'd be nice if you were as close as possible to what's flying away, so you can do a quick and dirty test. Does this compile? Does it run? Does this version of Bash have this tweak or something like that? It's just nice to have that there, so you don't need to go and jump onto a avionics bench to go test what you're trying to do. Internal meta layer reuse, right? That's because you're trying to allow other development projects within the company to product line their stuff. What's best practices around managing internal meta layers? There's some unsolved problems there. What's the best way to do that, to product line all your dependencies? And then of course, project repository code editing. If you imagine that you've created BitBake recipe for thousands of dependencies or hundreds of dependencies for a project, you open the source code for that project, you're going to get a lot of red squigglies if you have entry code. And so what's a good way of creating a single source of truth so that the BitBake recipe knows its dependencies, and whatever you're using, Ant, Maven, Gradle, CMake, Bazel, whatever, you don't get all the red squigglies, but a single source of truth, right? That's still sort of an area of tension for doing large scale development, particularly in the non-real-time space, but in the certified environment, and probably outside as well, how you manage that. So those are some unsolved problems. I'd love to hear people's input on those. So with that, that's what I've got. Thank you very much for attending. And Min, I don't know, do we have time for questions?
Yes, we do. In fact, I see
Okay.
a couple on chat. You want to start with that?
I can do that. Hold on, let's see. Okay, there we go. All right. Let's see. Oh, thank you, Steve. RTCA is Radio Technical Commission for Aeronautics. The word commission, for some reason, escapes me. Okay, Igor Stopa, says, why don't you share the shared state of the nightly build with developers instead of each of them creating their own shared state? That is a really good question. Some degree, couple of ways of answering that. So haven't gotten around to it is one argument. It requires some testing. The other part is a lot of times you want the developer to be able to work offline. So maybe when they're at home, off the VPN, that kind of thing, they would still have to download it. So just, having a way to rsync it to your machine would be beneficial. So, I don't see any reason why that couldn't be done. The other part is if you start your desktop running at night, it's really kind of a low overhead way to create your own cache. So it hasn't been a pain point enough to get us to do the work. But yes, I agree. It is something we should be doing. Okay, what is the update mechanism? Do you refresh the entire images? What happens to the old state? Okay, I'm not sure what happens to the old state, but and when you say update mechanism, I'm gonna assume you mean from one version of one Yocto release to another, and we call that floating up. So from hard knot, for example, to Kirkstone, forward team of developers will make all the low-level changes to change from hard knot to Kirkstone, and they'll just go through a lather, rinse, repeat process to deal with all the errors and bugs and warnings that crop up when you take advantage of all the recent development. And then that will be checked in, and then an announcement will go out to developers. Okay, do a git pull on the clone on your desktop, check out this branch, and reprovision your environment, and off you go. Do you reflash the entire image? I think you're talking about on the avionics device. And so, yes, you wouldn't call it flat. Like I said, a lot of the stuff we're doing is not real time and firmware style. So it's a little different from what you're probably imagining. We have a data load process. So we have effectively a firmware image that acts as a basic bootstrap environment. And then we can field load updates, and we do. And so that would just be a binary software package that's sent out to the fleet after it's certified and goes through the process. And there's an electronic way of getting it out to the fleet and loaded. And let's see, question 3, have you considered Clear Linux? No, I have not considered it. I don't know. I wouldn't say too much investment in Yocto. If Clear Linux does everything the Yocto OpenEmbedded environment does, but better, or it has some features that are just too irresistible, then yes, it's worth considering. But pragmatism wins. Yocto OE did what our homebrew system did times 100, way better. So it was an easy sell to throw it away and keep going. I think that's all the questions Igor had. Are there any other questions? Okay, yes, you can, right, I agree. You can generate, so comment for shared state, rsync state, you can generate signed shared state, yes. And that's definitely something, it's a big enough thing that we would have to put this is a task we're going to give it to a developer, and we're going to solve the shared state problem and make it available. So that is a thing, and I agree. Thank you for that. And then let's see, do you specify a minimum build machine baseline for hardware platform security features, e.g. TPM? Yes, there are, that has more to do with the avionics device. So we'll call that the hardware substrate. Depending on the avionics device that we're building for, it may or may not have a TPM. So yes, that's where that information would come from. And then you can virtualize a TPM. So that would obviously fit functionally. You want to have the virtual version and the flyaway version. And so that would be specified against the hardware architecture, the whole 9 yards. And then Linux Secure Launch, so 2.0, Linux Secure Launch, DRTM, trench boot for higher assurance of the build environment. Okay, we don't qualify, so DO-330 is for tool qualification. We don't generally qualify the tools. That is very labor intensive. So what we do is we roll up in our test and validation process, we say when we test and validate the final product, whatever DAL level we're doing, that by implication validates the tools used to get us there. Now, you better hope you can show traceability through things even as simple as, are you checking in a recipe with the SHA-256 sum in it of the source bundle, so you can show a logical connection from A to B to C all the way to the upstream source. You better hope you did that. That's reflected in what I've described. But it's easy to say when you've passed all the tests and they are rigorous, you can by implication say that all of the tools used to build that are implicated in all those tests passing. If we wanted to take credit for certain stuff and have less of a testing burden, then of course we would have to qualify the build environment, the tools, et cetera. But then that reduces our flexibility with those tools, and it makes it very difficult to innovate. Like, there's been 2 questions already on the shared state thing. If I said, oh, well, we've qualified it, no one wants to pay $1 million in funding to do that, right? It just doesn't make sense. So it's just easier to roll everything up into the test validation at the end. Okay, let's see. Which layer management tool for Yocto would you recommend? There has been announcements about a tool which is planned to be directly integrated into BitBake by Alexander Knavin. Are there any updates on that? I don't know. I'm not going to click on that link right now because in the middle of our presentation. I know I just recently submitted an RFC, a request for comments for a way to update setup layers.json. And so Alexander and I are discussing back and forth on that. He's making some really good points. I think he sees some of what we're going for. I know he's asked some questions about some other nuance. So I'd have to look at what you're describing. I have seen distro management. I know Garmin has some there's some other distro management frameworks. Those looked great. I definitely don't want to knock any of them. They looked very tightly engineered. I don't want to say over-engineered because I didn't use them and I have no right to say that. But for our environment and within Boeing, we actually have separate teams working on distributions, like teams reporting through different management, even business unit structures, but we all want to work together. So having one framework for doing distribution management is going to be problematic. So what I described in this presentation is a looser coupling, but getting, I would hope, the same result. So I don't have a good answer for layer management tool other than to say, we use setup layers. It works really good. And I promise I'm going to copy and paste this link and I'll take a look at it afterwards. I might have a comment on it. Okay, let's see. Are the patch levels SBOM binary? Let's see. Rich Prasad says, are the patch levels SBOM binary fingerprints of the build test machine recorded alongside accredited artifacts? Excellent question. Yes. Like I said, we have to, if it's flying out in service, and it could be flying out in service for 30 years, if it's flying out in service, we have a burden to be able to rebuild it at any time. We hope that doesn't happen, but we assume that it could happen at some point in time. So yes, we take a snapshot of the build dev appliance, and that's permanently archived. And that's why we want to encode, and we want the build to be very simple with all the dependencies easily managed, because that's permanently archived. And somebody who will be around, hopefully long after I retire, needs to be able to reproduce that build. Yes, we permanently archive those virtual machines. That's another reason why really big on virtual machines, really not big on using Docker for these tools, because virtual machines, if you understand how virtualization works, it requires very little in the way of dependencies. There's a lot of hypervisors that will run your virtual machine, or you can even paste it to bare metal and run it. Docker, I don't feel confident that you're going to be able to run it anywhere in 30 years. So I see very little use for using Docker containers in this environment for what we do. Don't want to knock anybody else's use of Docker, but as you can see, our environment requires to be able to rebuild. So no, it's not something we're gonna consider, but definitely yes. Containers, yes, absolutely. Yeah. Let's see. Okay. Thanks, Sebastian, for reposting that link. And then Rich says 30 years. Wow. Which hypervisor has a 30-year support contract? hopefully an open source hypervisor. Well, yeah, of course, right? I have no idea. I don't know what's going to be around in 30 years. I don't think anybody else does either. But I know that we can run DOS still, right? You know, if BIOS is not that complicated in the big scheme of things. So you can run old versions of operating systems. It's done all the time. So having a virtual machine does make your life easier. I happen to personally believe that even for non-aerospace applications, a lot of what I talked about, particularly focusing on virtual machines, will save you. But you know, some people think it's just easier to use Docker, and I totally respect that. And yes, we know that there's actually worth looking into if you're working in certified in on certified software. Zen actually has they're coming up with a certified version. It's not to DO-178, but it's to other automotive industry standards. So there are some artifacts with Zen if you're trying to look for a certified hypervisor.
Great.
Looks like we got one more. Igor says, do you think this approach will require tweaks, enhancements to support higher levels of safety? Absolutely. So when you get to DAL-C, you have to do what's called low-level requirements. And to quote, yes, Matt's right. To quote Steve Van der Leest, to quote Steve Van der Leest, you have to define your requirements in a way you could almost write the code just from looking at the requirements. You don't even need to know the big picture view. So yes, many, many tweaks. Particularly, one of the difficulties is, let's imagine you want to do a DAL-C B or a Linux kernel. Okay, obviously what you're going to want to do is triage the problem, get rid of as much source code as you possibly can, because that's just code you don't have to certify. Okay. But you also want to be able to maintain, if you want to product line it within your organization, you don't want this to be a one-off. So you want to maintain fidelity with upstream. And so that's a really good reason why your Linux kernel BitBake recipe, you just include thousands of patches to patch out all the things that you don't want. What's left is a bare skeleton with only what you need, right? And then you can then get into changing what you need to, testing, that kind of thing, so that when a kernel update occurs, you can see where the patches no longer apply cleanly. That gives you at least a really quick first pass view of how much change has occurred, how much impact that's going to create on you. So yes, there are many, many tweaks, and testing also is another one, which we can go into probably in a different presentation.
All right, we're at 1 minute after the hour. Thank you, Chuck, for a very great talk. And thank you all the people who joined the call, and thank you for your participation. As I mentioned on Zoom chat, to continue these conversations, please join the ELISA Project Aerospace Working Group. So I put the link there, and we have other working groups that hosted by the ELISA project. That's on our website. So thank you again for the talk, Chuck, and we look forward to everybody's participation in the ELISA project to continue these conversations. So thanks again. Bye.